Good morning, everyone. It's really a great pleasure. I'm very honored to be invited here. Thank you very much. Very honored to be there for the very special Congress as well, celebrating 30 years of this community, building tools and technologies and framework to help developing the best software for future technologies. I think it's how it's stated on the website. And so it's great because this is also our big aim in the Trustworthy System Group in Australia, where we are changing and we are helping the world change the way software is built so that it can be truly trustworthy using formal verification. And so today I thought I'd take the opportunity to discuss a little bit of these successes in getting all the way from verified software, in particular the SEL4 microkernel and everything around it, up to actually having it deployed in multiple sectors around the globe, and all of the different aspects that this may involve. So, to start with, and knowing the challenge of being the first in the morning after the social event, I'll start with a very easy question so that we get everyone a little bit wake up. The question is the following: who believes that is true? Who believes computer programming is an exact science? Can I have a show of hands? Who thinks this is true? Who thinks it's not true? Okay, it's just checking who's, just not listening or asleep still. So this sentence comes from one of the seminal paper that we all know or should know, which is from Tony Hall. And it tells us that, in principle, we can have all the properties of programs found out from the text itself purely through deductive reasoning. And of course, that the most important property about that is that whether the program accomplishes the intents of its users. So for about apparently 50 years, we actually have a solution to get software with proof about their correctness, which is, the topic here. But even back then, we were warned that this would not be easy, that it would only be possible once, or widespread, once, a lot of much more powerful proof techniques would be developed. But then, with the idea that once we would have that, we could have the advantages of having a proof about a program really outweighing the difficulties of doing so. And this is really inspiring, and this is what I like to call the dream that we hope all we're sharing here. This is the dream where, software system would only be deployed, especially in critical systems, if they have been going through formal verification. The dream of a world where verified software just becomes the standards that is produced by industry, and that it becomes legally considered a negligence if you actually start deploying software that is not verified. So this is the idea of a widespread verified program that, as a community, we've been working towards. And so in this talk, I'd like to continue a little bit about taking a status of where we're up to towards achieving that goal, and in particular with all of the recent amazing progress in the recent years, but why we're not fully there yet. And I'm going to take not the usual standard angle of what is the barrier to adoption and things like that, but just more like taking stock as a community. And then I'll go into a bit more details about the story of our main technology, which is SEL4, but that comes with a lot of infrastructure around it. And as Carrol mentioned, looking at both the technical aspect, but something that is a little bit more unusual maybe, which is all the social aspects. So this will be quite, like a higher level, non-technical part. Okay, so in terms of the first thing, which is the progress to have widespread verified software. So I'm not going to go into the details of the recent progresses. We've heard a lot about that along all these days at this Congress. But mainly what I have seen as a shift, especially in the way we formulate that, is how do we actually convince people about the use of formal methods when you deploy software. And actually in some of the conferences recently, I started to hear things like, how do you build a business case for formal verification? How do we have, we solve a marketing problem for software verification? And this basically goes into, look, we're all convinced here, but somehow there are much more decision makers than the technical community, and we have to get them to convince people that not necessarily have the background and so on. So that's quite interesting, because it seems that even if we have the solution, even if we're convinced, there's still something to convince other people about the benefit of it. And so what I'd like to, I'll try to have an experiment here, which is, I'd like to ask you in this room, if you had the experience of having to convince someone in few words, in a one sentence, why should formal methods being used when you deploy software? What are the 2-3 keywords that people are using? Who had the experience of trying to convince people in professional or in personal, in social circumstances? Yes?
Oh, you're asking what they were?
Yes.
They didn't work.
They didn't work. No, I was asking what were the arguments? What are the usual things that people would say? Yes?
I'm in an industrial context, so save money.
Save money. That's okay. That's a nice one. Other ones? No? Okay, so I think one of the things we hear are things often from the technical community about the high assurance that you can get, the fact that you get the mathematical trends that you might not get through testing and other means, that you might avoid bugs after deployment and that may you save money, that you can avoid security leakages, that you may avoid catastrophic failures that can bring financial losses, loss of lives, and so on and so forth. And this seems to have been a lot of the argument that were deployed, and that was something that was also mentioned. So I was mentioning that I heard talks around the business cases, and that was from Amazon actually talking about how they convince internally of using formal verification. And actually, the idea is that when you have this kind of argument, there's always a yes, but. So Carrol was saying it never works. So what are usually the yes, but? What do people answer to those questions? Yeah, it's great, all of that, but what?
Well, I think I'm not going to give you what you want, but it's usually they simply do not understand the law.
Okay.
If you want your programs to be correct, you want them to work. Okay, it doesn't work.
So they just assume that it doesn't work, or it assumes that it should be working by itself?
I think they think it will never happen.
Okay, are not convinced that it's a reality. Okay, that's a good one. Any other person wants to share what they hear when people are not convinced about? Yes?
Can't get regular engineers to use it.
Yes, hard to use. Okay, that's another one. That's the barrier of adoption that we heard a lot. Yeah, that's true. Any other? Cost. Yes, it costs too much. So these are kind of the things. It's very costly. I have my time to market. It's not usable. You can actually end up with things that are not performing enough, that are cannot deployed, and something. It might not be scalable. The other thing is also sometimes they just say, well, others are not doing it, or convince me that actually I should be really doing it. Why should I do it? And somehow, if I come back to that paper, there was 10 years ago a retrospective that Tony Hoare did, where he came back about what happened in the last 40 years since this paper, and acknowledging the progress I mentioned in terms of the automation and so on. But in terms of the second one of outweighing the difficulties, and in particular in the cost, and here the cost mentioned here referred to the cost, say, of really expensive lawsuits when you would get a software embedded and then would lead to catastrophes. And the retrospective was saying that whenever this issue would come to court, the defense of the state-of-the-art practice would prevail, which means, like, actually I use the state of the art. I use what is, like mostly available, that I can actually embed, that actually engineers can use, that, most of the community is using, all, in the industry is using. So my angle here is to say that really what needs to happen, and it's, I guess, not controversial, but it's basically that we need to become the state of the art. So that's just, like to summarize that this is what really is missing, if you summarize in one state, is that we need to become the standard, the state of the art. And there are many things that need to happen for that on the technical side of things. But when this happens, hopefully the answer to why should it be used should be why not. Like, would there be any reason why not to use it? Why are your reasons not to use it? And people feel like, oh yeah, actually, why am I not using it? Okay, and so this can somehow be split into, when you argue for formal verification, the good reasons to say yes, and then remove all of the reasons to say no. So that are the two angles that we can work towards. And you could argue that ultimately both of them would come to a cost in some factor, like reducing the cost of having to have recalls, or actually reducing cost in production. And this is something that was mentioned in that paper 10 years ago, which was the incentive of reduction of cost. So this is actually the best case. You could even just, if it's just, you can prove that it's going to be as costly or as transparent. We heard quite a bit of, if it's transparent from the decision maker, that to get benefit, you don't lose anything, you don't take more risks, and so on. This is where it's easier to take that decision that, yes, this is something that we should be doing. And so, in terms of the reasons to say no, this is very much where we need to become the state of the art. And this is where going into, like, all the things we hear around here, like automation, education, all that areas of work. And I believe that a little bit on the reasons to say yes, rather than having, the argument, the technical of, like it's a mathematical proof and you can't imagine how much assurance you can get. There's also this discussion that I heard quite a bit. It's sometimes if you have verified software in the verification community, we never say that, it's never going to crash and things like that, even if the media wants to say that. And so sometimes if actually then you end up having something that has an error, then the decision maker would kind of, cross out the whole field of saying, you see, it's not working. So it's really like trying to convince that you get like an assurance that is unprecedented, but more powerful is actually sharing, they are doing it and this is what benefit they got from it. So this is more or less kind of like the introduction of making sure that towards this goal, we as a community are working to make it really the state of the art and sharing our experiences, our stories around it so that we can have more reasons to say yes and removing all the reasons to say no. And so with that, I'd like to go into sharing a little bit of the story that started with the CL4 and then went a bit further, and I'll explain what all this is. And so in that second part, I'll concentrate a little more on the technical aspects with that. So in just one slide, it was basically coming about 10, 15 years ago of producing a verified and performance microkernel, and I'll explain in the next slides more or less what it is, and having that kind of central critical piece of software for any kind of embedded system or any software system being out from originally a research project, and all the way when it is now used in like a number of sectors. So like in automotive, in self-driving cars, for instance, in medical devices like insulin pumps and stuff like that. Some of them are more research projects, some of them are more on the deployment side of things, in space, in satellites, in aviation, so especially in unmanned helicopter, for instance, or unmanned vehicles and so on. In the military space, including, for instance, in information systems where you want to isolate networks that have confidential information from the places where there's, like public domain. security dongles where you can have, a USB stick running on SCL4 that, gives you some secure communication, industrial systems as well, and so on. So the story of making something that started as, like a research project, let's solve something that, seems impossible, to actually all the way to making it adopted by third party and used by other parties is something that I wanted to reflect on here. And so for that, I'm basically going to give you a little bit of the timeline of how all of this progressed. And as I go, I'll mention what, in the retrospective, we believe were the key factors that started to convince people of using it. So at the very beginning, it all started just with a general idea of when you build software and you want to trust that software, you want to minimize the trusted computing base. So that was kind of the general idea. And this is all where the idea of microkernel came from. So the idea is rather than having a big piece of software running on your hardware or even having monolithic big operating systems, you actually minimize what is at the core, at the connection to the hardware. Technically, it means that this is the piece of software that runs in a privilege mode, so it has higher privilege than everything else, and you minimize what is in the kernel. You minimize any services to really what strictly need to be in the privilege mode, and everything else run on top of that. What that gives you is that you can have true control accesses. You can really make sure that everything you run on top, you can isolate it, you can componentize, you can control those accesses because you force any communication to go through the kernel. You force any access to resources to go through the kernel. But the first question is, what about performance? If everything has to be going through the bottleneck of the kernel, what about performance? And so that was the research about 20 years ago, probably, that started with the ancestor of the Trustworthy System group, led by Gernot Heiser, so from the operating system side, to basically prove that, yes, microkernel is not only a great idea in terms of minimizing the trusted computing base, but you can make it performant. And this is where the next challenge came in and said, look, okay, but now you have this piece of software, you've minimized it, but now it's at the core of everything. It's the most critical part of your system. If it has any bugs inside, this is what is going to make the whole system fail. And so this is, what assurance that you have that your microkernel is working properly. And microkernel was really the perfect target, not only because of the size, but because of how it can give assurance, not only about itself, but about the system that you can build on top. The fact that you can then isolate big part of your application stack. So when we see things like the car hackings, where people can get control of your brakes through the entertainment system, this is because it's missing this isolation. So when you get isolation through a microkernel, this gives you assurance not about only the microkernel, but the fact that you can actually ignore a big part of your software stack, like your entertainment system, while still preserving assurance about your critical part, like the brakes in your car. And so in terms of the assurance, that's where the actual verification of SCL4 started. That's where, so Gernot Heiser, that operating system leader of the group, worked with Go and Klein and said, look, I want a microkernel that is verified, but I don't want to lose any performance because I want this to be used and deployed. So this was the big project that created the SCL4 microkernel and its verification. And so the verification, the first big breakthrough was to do that full verification of an entire microkernel, showing that the C semantic was preserved, refining the high-level specification, all done in a mechanized theorem prover in Isabelle, and showing that basically all of the behavior of the C code are the behavior of a specification. And that was 10 years ago. So we just celebrated the anniversary. That was a big breakthrough in both of the communities, formal methods and operating system. And the next question after that was, okay, what about your spec? How do you know that your spec is correct? You're basically, some people were saying, yeah, you've shown that it's as bad as your spec or that you have as much bugs as in your spec. And so this is where you can do, of course, further verification on top of your spec. There's always a boundary We all know it as formal method practitioners that it's really important to state your assumptions. I always say that the assumptions in formal verification is the added value, is where you can say, look, I've covered all of this. Now you should be looking at the assumptions. This is where, if there's something going wrong, this is where you should go, especially in security where, it's always about the weakest link. So I think the assumptions of formal verification, when they're explicitly stated, is really an added value. So here is, we proved the typical security properties, in particular, confidentiality and integrity that proves that isolation. So what that proves is that if indeed, when you set up your system, you don't trust a big part of software, you don't give it the access rights, and you prove that the kernel will prevent this part of the software to access, let's say, the memory where the encryption keys are, and so on. And then the second question was the compiler. How do you make sure that you don't have any bugs through the compiler? And so we had a proof down to the binary of the, so basically giving the guarantee at the executable code. So this was kind of the first big phase where we ended up with a very thoroughly verified and performance microkernel. And this is where it was so far very much, like on a research breakthrough, but people starting to have a little bit of interest on the more like the industry area. But the first questions there started to be, okay, can you actually use it in real system? Can I build systems on top and so on? And so the next big projects that made a really big difference was the DARPA-funded HACMS program, working on high assurance cyber military systems. Here, we basically embedded SCL4 on 4 types of autonomous vehicles: helicopters, trucks, robots, quadcopters. And we could show, A, that it was really performant, you could actually fly the helicopters and so on, and B, that you could actually protect against cyber attacks. So in that project, you had a red team, so professional hackers that are paid to try to hack all these systems, which they do, like they manage to get access to the critical part of your system at the beginning of the project, and they can take control over the vehicle and bring it somewhere else. And towards the end of the project, we had these big demos we could, have flying helicopters and the red team trying to get access through the non-critical part, like the camera or the Wi-Fi access of part of the system, but never being able to then propagate that vulnerability and that compromise to the rest of the system. And I think this was really quite a big step in showing that, that's what we heard, that people started, oh, actually, formal verification, on real systems, that's great. And about the same time is where people wanted to try it, wanted to play with it. And this is where we got it open source. So the open source only happened about 5 years ago. And this really changed and impacted the fact that we managed to have third-party use later on in the adoption. Because the microkernel is only a part of your system, and therefore it's not like an entire product and so on. So you need really people to be able to use it, build systems on top, and so on. And finally, in that phase, there was also this question of, okay, that's great, but do I really need to start from scratch? Do I really need to have my existing system, put it in the bin, and start from scratch using the system? And as part, actually, of the DARPA HACMS program, we had this idea of cyber retrofit. So basically, retrofitting an existing system, and that's what we did with the Boeing helicopter in collaboration with Boeing. So actually, Boeing did most of the work with our help in terms of how you architect your system, because this is where you need to re-architect progressively your system in a way that you first, be able to run it on top of SCL4 and then start to identify what you can isolate. You can run a big part of your software that is not critical on, a virtual machine, and then start to identify what is critical and start to, get those components out and so on. And I think this was also key. We had a few further projects on that kind of retrofitting. And this, I think, helps with convincing people that it's not something that is too brutal in terms of a transition to using something that is that has more high assurance. So that's kind of the second big phase where people started to see that, okay, well, actually, I could actually, especially when I'm on my new phase of my product and I'm thinking about the next version, that I could think about transitioning to something that have more high assurance. And there's all the question that we also keep working on and having an infrastructure to help them produce those systems, like from the architecture level, helping them retrofitting their systems. But of course, as customers or people that want to use it, they start to be demanding, and they have, like, oh, great, but now can I have this and that? So the first thing was about, oh, but my platform is not really the one that you've verified on. So we verified, all of the verification I talked so far was on the ARM platform. So we started to look at, oh, okay, so if we port to other platforms like Intel or the new RISC-V open platform, so we started to change our code so that it runs on those platforms, but then, of course, starting to have the updates of the proofs that needs to be done as well, and how do you deal with this evolution of the proofs? Same thing about features, people wanting more features. So, for instance, the two big ones that we've been working on and are still working on, the first one is multi-core. So the first verification, all of the verification so far was on unicore, and so how do you deal with multi-core and how you can port the assurance that you can have. The other one is MCS. It stands for Mixed Criticality System, and that's one of the more recent research breakthrough as well, that got the Best Paper Award in the systems community. And this is to consider time like a resource. So the same way, if I don't trust a piece of software, I don't want to give it read or write access to a piece of memory. Well, here, I want to make sure that the piece of software will run in its allocated budget in terms of time. And so I can also consider time as a resource that the kernel can control and then prevent an application to overrun and prevent another application running. So, of course, as usual, there are the two things, updating the kernel and updating the proofs, and what does it mean in terms of the assurance? And finally, can I have more guarantees? So a lot of the things that were in the assumptions in here are things like timing channels. And one of the person in our team are looking at the finding the vulnerabilities, so like Spectre and Meltdown. So Yuval Waram in our team is working on those discoveries. But also, how do you then get principal mechanism on the kernel side of things to be able to identify, prevent, mitigate timing channels. So all in all, and the last thing, of course, all of this is at the SCL4 level still, but then when you build entire systems, this is only one piece of the solution. You might have in your application things that need to be trusted. A filter, a downgrader, like all these systems, this application software that needs to be trusted. So here, we're looking at ways to make it easier for people to develop those application-level software. So, for instance, we have a few projects, Cogent, KKML, MicroVM, that are looking at domain-specific languages where you can generate as much as possible of the proofs of correctness so that it's make it easier for people to prove properties on the system, on the application level as well. All right, so basically, as we were trying to get all of these deployed, we keep creating more challenges, both research challenges and also engineering challenges. So at ITP, like a month ago, I talked about the challenges of dealing with, we have about 1 million lines of proofs about a moving target. So basically the code keeps evolving, and that creates a lot of engineering challenges that we have to deal with as well. But my main message is we have to deal with those challenges if we, like getting the impact and the use that people are demanding, and make sure that when you do verification about software, you need to be able to deal with an evolving target, because otherwise your software very quickly becomes obsolete. So you need to be able to listen to the demands of the customers or market. Okay, and so more or less in the technical aspect of that story, it was to, when we targeted the verification, what the few things that made it really suitable for adoption and third-party use was to keep the performance, to make it open source so that people can try it, providing some way of retrofitting an existing system rather than forcing people to have to completely start from scratch, and finally keep working on those grand challenges. And those grand challenges, about doing more platforms, more features, more guarantees, working on the cost effectiveness, like producing the proofs automatically, answers more or less the questions I mentioned in my first part. So less reasons to say no by being able to say, look, you want that platform, you want that features, and so on, and then more guarantees, so more reasons to say yes. So that's more like coming back to that first part. Okay, so this is for the second part, more on the technical aspect. There are way more to say. I'm happy to answer questions afterwards if you want. I just wanted to give like a quick overview. And now I want to move on to like another aspect, which is something that we probably discuss a bit less, like, so not a technical at all, but it's more like on the social aspects. So here, I want to come back to the requirement I just mentioned in my previous section. So in my previous section, I was saying, look, if you were given that task, that mission of leading a project where you have to have a piece of software that is verified and performant, that needs to be deployed and needs to be listening to what the industry sectors or the companies would like to see, and that you keep extending to new feature, to new research challenges, to new engineering challenges. So let's assume that this is our mission. Should we accept it? This is the specification, right? How do we implement that? So the question is how? What is the first thing that we need to be able to achieve this? Any guess? People! So that's, of course, the first thing. So we need people. We need people. Okay. Great. What kind of people? Qualified people. Okay. So if you would put a job ad, we just qualified people. But what kind of profile to be able to do that kind of piece of work? Like, if you're probably going to have different profiles for that because it goes from the research challenges, engineering challenges, extending to new features, and so on. So what kind of profiles do we need? Come on. We're all in the same mission. I'm not the only one here. Come on. Yeah? Sorry? People that have multiple skills and so on. Yeah, that's true. Yeah. Okay, so in a very, very broad sense, you can think about having both researchers and engineers. Okay, you have to have that. Like this is, like you would have research challenges and you would have engineering challenges. And you really need these two profiles, right? Usually you also need students to help the researchers and have, people that were working on the research side of things as well. And then in our case, we're looking at doing formal verification of operating system code. So we also have a combination of disciplines. So you might be looking at, okay, in terms of who are the people I'm going to look for, you might have people in the formal verification world, you might have people on the operating system world. Okay, so more or less, this is what we need. We need people from the research, from academia, some people with engineering profiles, and some people with OS background, and some people with FM background. Ideally, you might have people that are good at all of that. And a lot of the things that I'm going to say, by the way, I should have said that to start with, is, like things that may seem very obvious to some people. I'm just sharing what we thought was the thing that made it work for us. And I think this also reminds a lot of the studies about, how do you reach, close the gap between, say, academia's work and industrial work? And how do you make formal methods work better and close that gap when it needs to be applied to an application domain like operating system, but it can be anything like networks and so on. And I think one of the things that happen when all of these descriptions are met is that it's always described as two kind of separate worlds. We're talking about that gap that needs to be closed. And it always has a feeling that, some work happens on one of the worlds and somehow needs to be handed over to the other world in some form. And so I think that one of the things in one word that really is important for us was to make sure that we're considering a one world, meaning that you don't have actually one group of researchers and one group of engineers or people that have the different disciplines coming from academia working with, say, an industry, but make sure that whatever the granularity is, in the smallest granularity, you always have that combination in a one single group. So this is how, but I think I haven't really answered it. I just had done one step of refinement between how do you achieve that requirement. The one step of refinement is, okay, we do one world, but how do you actually do that in practice? And again, I'm just going to share what made it important for us. And I tried to summarize it in three kind of themes. The first one is the tight integration. Like, make sure that actually you don't reproduce those silos within the group, that actually people work like really tightly together, that the interactions are actually really frequent to avoid that kind of handover feeling inside the group. And then the communication. We're actually talking about getting people from very diverse backgrounds, different disciplines, different ways of working, different incentives of what is important for their career, and making sure that they can work well together to be able to achieve that one shared goal. Okay? So these kind of the three things that I think were really important, or are right now really important, to be able to continue to solve those challenges. So the tight integration, the frequent interactions, and the good communication. And now I'm gonna again refine, and give more concrete examples. So that's like really reaching kind of an implementation. And this would just be anecdotes or examples of things. I'm just thinking that like sharing a little bit of what may worked and didn't work might be useful to others. I'm not sure. So the first thing is, as I said. We did those pictures by, like saying, okay, who's on which team? And actually some people were just saying, look, can I be actually on both pictures? Because I think I'm kind of considering myself as a bit of both an engineer and a researcher. Or some people are actually, coding systems, coding the microkernel and doing, helping the formal verification as well. But the main idea is that we're a single group, okay? So, and even within the group, like we may have teams and so on, but even at the granularity of projects, the projects always involve people from all of these areas. All of our project would have some bits of research, would have some bit of engineering, would have some bit of that needs the operating system expertise and some bits that need the formal verification expertise. And this really allows that tight integration so that we make sure that all of these pieces work at every granularity together. And then more in terms of practically putting that in place and what needs to happen at managing and planning things for the group, it's important to have a shared vision and having a culture where people feel that they're progressing as a team. Rather, as I said, we have different incentives when we are a researcher, when we're an engineer. And so making sure that everyone sees the benefit from the entire group to grow. And that's something that needs to be actually things that, as leading the group, you need to be really proactive and have specific actions to make sure that that happens. So a few examples of those. We have this kind of strategic sessions where we make sure that it's not top-down, but everyone can see what the shared vision is, can contribute to it, and the kind of feedback that we get from people is, firstly, wow, I see that what I'm doing on my small corner, on my Isabel file on the day-to-day, actually fits with what everyone might be doing in that big grand vision. But also, I have the opportunity to say, well, why don't we actually go into that direction, or like making sure that they really share that vision. In terms of making sure, like the culture is a really hard thing to enforce. Like it's something that needs to be really monitored in some way. And so we actually run sessions on a lot of those themes for everyone. So on growth mindset, on mental health, on active listening, on life balance, to make sure that everyone feels that they're looking after each other and making sure that, this is the condition for people to really grow and feel that they are their best to be doing that work. In terms of diversity and inclusion, I'm saying you put together the most diverse people, and in particular in our fields of people that might have very strong personality or maybe very shy or maybe introverted. You actually actively look at after making sure that everyone feels that they're being looked after, and a lot of social activities as well. So this is not uncommon, but I'll mention one thing that we do maybe differently than elsewhere at the last slide. And so that was more like how a few examples of things to make sure that the integration is really tight. The second point was more on the frequent interaction. So how do you make sure that actually people see each other and talk to each other? And this is actually challenging in the world where people want you to be very distributed and we're all modern and everything, but what really helps is when you're in a single location. And even sometime in a single floor. We had been in a single floor, we had been in 2 floors, we had been back in a single floor. I can tell you that when you're not even in a single floor, you have to proactively look at ways for people to talk to each other. Otherwise, they just, start to have those silos. So this is just the floor plan. So you just, make sure that whatever the path that people have, that this will create natural interaction. And the joke I like to say is, I don't know if you see those paths, but they all lead to somewhere. What would that be? The coffee machine. So I was joking, saying like, if you want to have a good project, if you want to have something, between something that is, like a bit engineering focus, can you actually do that kind of projects with people that don't see them often? So the coffee machine is really the place where you just happen to meet every day and happen to start those conversations. And this is kind of forcing the interaction that you wouldn't get. And as I said, we get a lot of, actually even when we hire people to say, oh, could I do remote work? We have tried it doesn't work. Like in these kind of projects where all our projects need to have, you have the proof engineer working on something and wants to change the code, talking to the systems engineer, knowing if that's going to have a performance impact, the systems engineer wanting to do a modification, wanting to make sure that it's not going to impact too much the environments that are going to be proved and so on. Ideally, again, these people would be kind of having both expertise, but this is something that is really that tight integration on the kind of everyday basis. The last thing is good communication. We're talking about people with different disciplines, sometimes even different languages in terms of, what they're talking about. A TCB can be a thread control block or a minimized trusted computing base. So how do you do that? Well, we are very strong in terms of making sure that communication is really important in the group. And this is to allow this shared knowledge. And what we do is actually we have these weekly talks, like in many other groups, but we basically, it's strictly every week, and we call it all to all. So what we do here is we say, look, whether you're the fresh grad student that arrived a month ago, and you just happen to be randomly selected for next month, or whether you've been the professor here for 15 years and you think that everyone knows what you've been doing forever, like every one of those have to make the effort of explaining to the others. And when I say to all, like it needs to be understood by everybody. It needs to be, and that's a challenge. I'm not saying we're always successful, but we give constructive feedback every time. We try to really make sure that we can have those conversations, and that creates that link that allow people to get interest for their project from other people, allow when they are the coffee machine to be able to say, look, like what you just said this morning, I don't think it's going to work for performance reasons and stuff like that. So this is really important. So that the new people that just join are not completely freaking out. We actually help them, so everyone get training on presentation skills. I'm really passionate about that, so we really make sure that they can know how to present, how to do the slides, how to do a pitch, how to explain their work in a level, how to adapt the technical level depending on the audience. And I'll come back just at the end as well on how we do that. And finally, of course, I believe very much on whiteboards. I don't know how many people have that has started to creep into your actual personal houses and having whiteboards everywhere. But at least at work, there's whiteboards everywhere. And here I just want to give a funny anecdote. So about 3 years ago, we changed building. So I was, we were just new location. And so I was going to those meetings with the architects telling us how they're going to fit the inside. And every time I was looking at the floor plan like that, I was saying, oh, have you put some whiteboards? Where are you putting whiteboards? So the next meeting they would come back, yeah, we've put your whiteboards, like they're here, and there are some in the meeting room. And okay, this is our fun room, what we call the fun room for people who have been visiting us. The fun room, management has trouble understanding the fun room. The fun room is where we can actually discuss research and technical topics. They don't understand that we have really fun in doing this. So we need plenty of whiteboards in there and couches and stuff. But then I said, oh, well, look at where people are actually walking. We need whiteboards much more. So we started to put whiteboards on the cupboards here. And then I was asking, oh, what about those cupboards? And every time I was seeing a wall, I was saying, can I please have a whiteboard here? To the point that at some point someone said, look, if we have a white wall, can we actually not put it white so that people don't start, scribbling things on it? Anyway, that's just a joke. And just as a QED, I took that picture to be able to put it before I left. We had a social afternoon tea. These two people were discussing a technical topic. And literally 2 minutes after, we had like 5 people around it. And including in that, we have 2 proof engineers, 1 professor in formal methods and concurrency, 1 student that is in operating system and a systems engineer and so on. So this is the kind of collaboration that really happens naturally if you put everything in place, you put everything transparently and it just happens. So this is kind of the summary. I just wanted to mention one important thing. I said one important thing of how we do it, and that might be different from elsewhere, I don't know, is a lot of this is self-organized and self-delivered. What I mean by that is it's, especially with technical people and researchers and so on, they don't really actually believe or trust or like things that seems corporate, that are imposed on them. And so, for instance, the training on presentation skill, all the sessions that I mentioned are things, we call it the boot camp. We have our annual boot camp. And most of the people that have never attended it is like, oh, really, should I go to that? And it's going to be an external person. It's all of us. All of us are actually telling each other. So mental health is given by someone in the team that wants to share about what would help these people. And this makes it much more trustable. People trust it much more when it comes to from their peers. Same thing about the social activities. Carrol was talking about those jelly beans. So we have all these, cookies and stuff like that in the kitchen area. But of course, they're organized by volunteers as well that, can ask you if you really like jelly beans, because people don't like jelly beans, but they much prefer like cookies and stuff like that. We also have our annual retreat where we go with all the families and so on. Same thing, self-organized so that we can choose something that means something to us, that means that we've looked after each other, looking at what people would prefer, and making sure that actually we start understanding each other. So that, I think, concludes more or less this third part of my talk, which was, again, very informal, but I hope was giving some insight of some of the aspects that are quite important beyond the technological aspects. And as to finish, I'd like to come back to, again, Tony Hoare's retrospective 10 years ago, saying that, even if there will always be a limit at which the engineers judge that the cost of doing the verification might not be greater than the benefit, well, these limits can be freely acknowledged by the scientists with no reduction in enthusiasm for pushing back the limits as far as they will go. So this is very, again, inspiring. I hope we're all here to enthusiastically keep pushing those limits so that we can all, as a community, keep working on making that dream a reality, using computers and so on, but not forgetting the human aspect and how all the social aspect can help in making this happen. All right, that's it for me. Thank you very much.